Good afternoon, ladies and gentlemen. Welcome to the Hipàtia Science Award Ceremony, an event that highlights the relevance of science for policy, the relevance of women in science, both of which should be obvious, but neither of which we can take for granted. I would like to thank the Barcelona City Council for hosting this event in this magnificent historical setting, the Saló de 100, the Hall of 100. You can notice its Gothic allure. This is where the Council of 100 used to meet from the 13th to the 18th century to govern the city. We will begin with the introductory words of Professor Ricard Guerrero, the academic director of the Barcelona Knowledge Hub of the Academia Europea. Dear Professor Guerrero, the floor is yours. Yes, please.
Well, thank you for coming, and representing the Academia Europea would be, in my case, the hub, and also Professor Maria Makarov, the president of the Academia Europea. I will be very, very brief. It's why we started the Hipàtia Prize, and what is the meaning. It was another idea by Andrew Masculin, because he said, well, I talked to the authorities, don't say anything, but perhaps 6 months after, I was asked by the authorities to organize a prize. So I decided in this time to put the Hipàtia, but it's not a prize only for women. It's women or men. But it's the several conditions in which the tribunal, every prize has 2 members chosen by the Academia Europea, 2 members chosen by the City Council, and 1 the President by agreement between Academia Europea and this. But the condition is, out of the tribunal, at least 2 must be women. Okay, and so it's a period, because it's difficult to have not every year, not always was every year. There are a cycle of 3 years. The first was devoted to exact science, the second was devoted to life science, and this is the third, devoted to humanities, social science. And the condition at least 1 person of the 3 in the cycle must be a woman. Now, in the first cycle, we have 2 women. So, but it's not, and we are putting the name of this philosopher, scientist, and that was killed because she was a scientist and a philosopher and telling this. So, thank you for coming, and I think you will see how it. And thank you to the City Council. Remember, because normally City Council are not devoting to science. And now, under the direction of Jordi Martí, is a specific plan for science and the academia. So thank you for organizing this for the first time in the City Council of Barcelona, in 700 years, more or less.
Thank you very much, Ricard Guerrero, for this introduction. Next, I will ask Maria Makarov, the president of Academia Europea, to come to the microphone to address us a few words. This microphone, please.
Deputy Mayor Jordi Martí, friends and authorities, it's a huge honor to address the Barcelona City Council as the new president of Academia Europea, and in this absolutely magnificent setting. Now, the Academia Europea was established in 1988 at the initiative of the Royal Society UK. The Academy covers 44 countries, the 44 European countries, and its frontier scholars and scientists cover all scientific disciplines. To date, we have 5,100 members, amongst them some 80 Nobel laureates. The Academy runs 7 so-called regional knowledge hubs, They are hosted by local universities or a national Academy of Science and Letters. And one of these 7 hubs is the Barcelona Regional Knowledge Hub, which focuses on research and other activities in Catalonia, in Spain, and in the Mediterranean region. The Barcelona Hipàtia European Science Prize was launched by the Barcelona City Council together with the Barcelona Hub led by Professor Guerrera in 2018. Within the framework of the Barcelona Science Plan, and as we heard, to highlight excellent research conducted in Europe and impacting societies. Indeed, today then, we are celebrating here the 3rd laureate of the prize to be introduced in the laudatio by Professor Hafer. Thank you very much.
Thank you very much, Professor Makarov, for these kind words. Next, the philosopher of science, Karl Hafer, ICREA research professor at the University of Barcelona, will introduce the recipient of the Hipàtia Science Prize, Professor Nancy Cartwright, with whom he worked closely for several years at Stanford University.
It's a pleasure to be here tonight. But first, I would like to explain why you're seeing me standing in front of you instead of Professor Genoveva Marti, who appears on the program. Unfortunately, Professor Marti is at home recovering from a very ill-timed bout of COVID-19. Fortunately, it's a very mild case, and she's doing very well, but she couldn't come this evening to be with us. And so somebody had to deliver the laudatio this evening, and the question is, why am I in her place? Well, as it happens, I am the husband of Genoveva Marti, but that has nothing to do really with why I'm chosen to take her place. As Giuseppe said, more relevantly, I am a former student of Nancy's. Well, I consider myself still and always a student of Nancy since 1986. I'm a philosopher who knows pretty well her works and why she's justly famous. And more importantly, like Genoveva, I'm an old friend of Nancy. So for me, it is an honor and a pleasure to tell you a bit about this year's winner of the Hipàtia Prize. Nancy Cartwright grew up in Pittsburgh, Pennsylvania, did her first degree at the University of Pittsburgh in Pennsylvania, in mathematics, not philosophy. But there she was exposed to philosophers of science, philosophers of physics, and this led to her doing a PhD precisely in philosophy of physics at the University of Illinois, Chicago Circle. She worked on the foundations of quantum mechanics at that time. In the early to mid-1970s, Cartwright rose quickly to prominence in the first rank of philosophy of science in America, thanks to her work on philosophy of quantum mechanics and, more generally, her studies of the role of laws in physics. She was offered permanent positions at various places, including Princeton, but she decided to settle in for her first main stage of her career at Stanford University in the west coast of the United States. There she stayed for several years, building up an outstanding community in history and philosophy of science. She was promoted to full professor at the age of only 42, and with the publication of her first book, she became recognized throughout America as one of the 3 or 4 most brilliant philosophers of science in the country, alongside people like Bas van Fraassen, Michael Friedman, or John Ehrman. What made Nancy Cartwright's work so prominent and so widely debated? Cartwright espoused a radical new form of empiricism, one that was centered on actual scientific practices rather than on philosophers studying theories or the very cleaned up reports of experiments that were mainly the things that philosophers tended to study at the time. Her first book was provocatively titled, How the Laws of Physics Lie. There's a play on words in there which I won't fully explain. But physical laws have always been extremely revered by philosophers of science. So how did Cartwright come to think that the laws of physics in some sense are lies? Well, she embedded herself in the laboratories of working physics groups that were doing the actual work of cutting-edge physics, like producing new forms of lasers or trying to prepare an experiment with a spacecraft to put incredibly precise gyroscopes into orbit around the Earth to measure the signature frame dragging effect of general relativity. So she immersed herself side by side with working scientists to see how they actually work. She took an open-minded look at the way that they worked, and based on that experience, she offered a reconfigured story about the procedures in sciences and what those procedures tell us about nature herself. She found, for example, that physicists more often spend their time building models rather than theories or refining theories. And she made a detailed study of many models produced in contemporary physics, leading to important papers which contributed to a shift in the attitudes and the focus of attention of philosophers of science around the world that has lasted until this day. As one philosopher of science from my generation remarked in a recent review of her 2019 book, there would be no philosophy of computer simulations or philosophy of climate science without Cartwright's trailblazing work on modeling. But to come back to that provocatively titled first book, why did Cartwright say that the laws of physics lie exactly? Well, when she took a look at how physicists construct their models and their instruments, Cartwright found very little reason for supposing that the most high-level so-called fundamental laws written in the physics textbooks truly state what happens in every situation in the physical world. Rather, to her, they seemed only to be true to the observable facts, to literally describe the observable facts, mostly in highly contrived circumstances, like, for example, physics laboratories, where shielding from unwanted influences and effects can be put in place. And those laws, so-called laws of nature, seem to be true in certain models that we construct on their basis, but the models only apply, again, to certain very constrained situations in the world. Out in the wild, in the majority of contexts, like this room, for example, one does not see with any clarity that laws like Newton's law of gravity, Maxwell's equations of electromagnetism, or even Schrödinger's equation of quantum mechanics are perfectly obeyed by every atom and every molecule. Instead, according to Cartwright, what we see is a variety of distinct causes at work, jointly producing the mix of order and disorder that we see around us. The same thing is true in our laboratories and our amazing technological creations, like cell phones that you all have with you. But there, we are able to constrain and control the causes at work and describe them with the mathematical equations of our best models. It's difficult for me to convey to you quickly how revolutionary her perspective was coming on the heels of the traditions in philosophy of science. Old-fashioned empiricists doubted the existence of causation and believed in regularities above everything else, i.e., equations and laws that are supposed to be true everywhere. But Cartwright showed that we have much more grounds for believing in causation than for believing in universal laws. And that all the sciences, from physics to psychology, really work with causation all the time, and that has to be the centerpiece of a proper understanding of science. So far, I've been describing what I think of as the first stage of Cartwright's career, her years at Stanford and the first few years at the London School of Economics, to which she moved in 1991. Cartwright's early work, while not universally accepted by all philosophers, profoundly influenced subsequent generations in philosophy of science. A significant portion of the community has accepted Cartwright's conclusions about laws of nature, about the centrality of causation to scientific practice, and about the need to study scientific practice by looking at its details from up close. And this has markedly changed the nature of the discipline of philosophy of science as a whole. Cartwright was not the only figure arguing for these shifts in perspective, but she was the most prominent and effective leader in bringing about the changes that happened in her profession. Now, by the time I became a student of Cartwright in 1986, she had largely shifted her focus away from the physical sciences to the social sciences, and especially to economics. Her second and third single-authored books developed detailed case studies in both economics and physics, and an increasingly important focus of her work was on the use of statistical methods for discovering causal relationships in the sciences, especially social sciences. This made it quite natural for Cartwright to join the London School of Economics, one of the most important centers of research of social sciences in the world, in addition to the fact that she was married to the distinguished philosopher Stuart Hampshire, and he wanted to move back to England at the time. Nancy Cartwright took up the chair at LSE formerly held by Sir Karl Popper, and there I see the second stage of her career beginning. There, Cartwright founded the Center for Philosophy of Natural and Social Sciences, which became an internationally prominent research center quickly and became the most active locus of philosophy of science research in Europe, and it continues strongly to this day. But at LSE, Cartwright's interdisciplinarity grew and flourished as she developed close relationships with economists such as Meghnad Desai, Amartya Sen, the economic historian Mary Morgan, and many, many others from a wide range of fields outside of philosophy. Cartwright's prominence and influence in Europe grew rapidly after 1991. She's been elected member of a great number of academic societies, such as the British Academy, the Wissenschaftskolleg in Berlin, and of course the Academia Europaea itself. Her prominence in North America, however, continued to grow in the 90s and 2000s as well. In 1993, Cartwright was awarded a MacArthur Fellowship, and in the late 90s, she became a part-time professor at the University of California, San Diego, where she's spent the winter term in most years ever since. She's been president or vice president of various philosophical societies in America, in Britain, and in continental Europe. I won't list all the honors, memberships, and awards that one finds on Cartwright's CV, but suffice it to say that the list is uniquely long and diverse for a philosopher. Now, in her LSE years, Cartwright's work developed and consolidated the image of science that I sketched for you a minute ago, and she extended her claim about the centrality of causation to a new metaphysics of nature itself, which fortunately I won't try to explain in detail to you. But the main part of her effort was increasingly directed toward understanding and improving the tools that scientists have for discovering causal facts, and for deploying those causal facts that they discover in the service of improving people's lives. The title of her 2007 monograph, Hunting Causes and Using Them, sums up her new research focus very well. The key here is the using them part. It can be hard to find a causal relationship with certainty, especially in the social sciences, but it's still harder to figure out how and when that causal relationship can be reliably used to guide economic interventions or social policies. This question has been at center stage of the third stage of Nancy Cartwright's career, which has been based for over a decade now at the University of Durham. Having quote-unquote retired from LSE, where she remains an emeritus professor, Cartwright founded another research center, the Center for Humanities, Engaging Science and Society at Durham. Since her arrival there, Durham has unsurprisingly been transformed into an important focus of philosophy of science research in the UK. Today, at the age of 78 years old, Cartwright herself has not slowed down one bit, and in fact seems to be more active and productive than ever. She has published one book this year already, and another one is forthcoming. One important focus of her work in recent years has been on the difficult questions about whether and when randomized controlled trials are really the gold standard of evidence, able to provide evidence that is reliable enough to guide public policy. Her most recent publications on this topic were co-authored with economist Angus Deaton, which gives you an idea about how she has come to have importance and influence in the social sciences. Before I finish, I really must tell you something more about Nancy Cartwright, the teacher rather than the researcher. Since the mid-1970s, Cartwright has trained and mentored a very great number of students, many of them now prominent philosophers in their own right. Just to mention a handful, she has taught Hasek Chang, who's now at Cambridge, Roman Frigg, who is at the LSE, local Barcelona boy, Jordi Cat, who is now a professor at the University of Indiana, Julian Rice, who is in Vienna, Mauricio Suarez at the Complutense in Madrid, and Sofia Evstathiou, who's at the NTNU in Norway, and this is just a very small handful of her students. But the important thing I want to tell you about is not who Cartwright has taught, but how she did it. She is one of the most generous academics I have ever known, taking her students under her wing and making sure that they learn all of the lessons that they need to become a successful and productive and virtuous philosopher. In most instances, her former students graduate to become not just PhDs, but lifelong friends of Nancy's. I'm fortunate to be one of them, and I'm honored to have been able to introduce Nancy Cartwright to you this evening.
Thank you very much, Professor Karl Hafer, for this speech. And now we have reached the moment, you can imagine a drum roll, the moment the prize will be delivered by the City Councillor Jordi Martí to the laureate Nancy Cartwright. Let me ask you both to come here on the carpet for the delivery of the award and for the photographs. Well, congratulations, Professor Cartwright. Now comes the time of learning for us, which is the ultimate reason to be of the Academia Europea. Nancy Cartwright will give us a lecture on modeling objectively. Professor Cartwright, please, the floor is yours.
Thank you. Of course, I'm absolutely thrilled, and I can't really believe that I've won this prize, and I'm very honored and very, very happy to be here. So thank you all so much, and Carl for this wonderful introduction and reminding us of our days together with Genoveva in Stanford. Let me begin here. The plan for the evening is that the overall theme is when models will be used to affect the world. That implies a special duty, a duty of care to model objectively. Okay? And the first part, I'm going to look at one of the standard senses in which the term objective is used. That to be objective is to be value-free, and objective in the sense in which you have a duty of care in modeling. To be objective does not imply that you have a duty to do value-free modeling. In fact, most of the time, I'm going to explain it's very difficult, if not impossible, to do value-free modeling. So value-free modeling is seldom possible. And when modelers when models are going to be used to intersect the world, values almost always must enter. There's no way to avoid it if you're going to actually be using your models, or someone else is going to be using your models to intervene in the world. Hence, modeling objectively is going to involve intertwining of the epistemic and the normative. And then part two, I'm going to talk about a duty of care and argue that when objectivity is a duty of care in modeling and other scientific practices, then there's a special kind of objectivity that matters, and it's called objectivity to be found. Important aspect of objectivity to be found is that it shares with most duties of care that they're seldom, what the duty requires is seldom explicitly listed, and you have to, there might be some exemplars, but not listed. An objectivity to be found implies finding the models for the right aim. So that's what will happen. And the third section, I'm going to give an example of the Vaillant Dam disaster. So in 1960, the tallest dam in the world was completed, the Vaillant Dam in the Dolomites. A fantastic engineering achievement. It was very highly praised for that. In 1962, a huge landslide went into the reservoir. The dam stood, okay? But a tsunami of 50 million meters of water, cubic meters of water, overtopped the dam in a wave 250 meters high, killing over 2,000 people down the valley. So this was before, and this is after. Okay, so that's the example we're going to talk about. This is Langroni down the valley after the tsunami. So part one, value freedom, it's often not possible. The reason that it's almost always not possible, particularly when models are going to use to intersect the world, is that modeling choices, the very choices you have to make in modeling involve value choices. Here's an economics example I'm going to use because I like it because it has values coming in at a great number of ways, so I can use one example to illustrate a lot of points. The UK 2006 Stern Review of Climate Change by the economist Nicholas Stern. So first of all, think about the choice of frame for a model. So the Stern Review uses, as many economic models do, a maximize expected utilities framework. Okay? That is, you're going to maximize the expectation of the sum of the utility of each individual with a weight for each individual. You're going to maximize the expectation of that. Now, to use this frame is clearly a value-laden choice. Okay. But so too would be choosing any other frame. I mean, one could maximize the welfare of the least off, being a prioritarian. There are many other things you could devise your model to do, but this one uses a maximize. So you can't actually make that choice one way or another without making a value choice. So just even to get a frame for modeling in these kinds of cases. Then choice of category to represent. Well, you're going to maximize the expectation of something that ranges over a bunch of individuals' I. Okay? Now, you can't sum over all individuals in the world to use, so that instead you use a representative agent model, and then the question is what categories of individuals get represented in the representative agent model. For instance, what about global south versus global north? Do we have countries? Generations. In the Stern Review, each different I, there was a representative agent for each generation. And whichever choice you make here is a value-laden choice because you're maximizing the expected utility of those representative agents. And if you're doing generations rather than global south versus global north, you'll get quite different answers. 3, a lot of times what you do masks other important features, in particular this one masks distributional effects. So representative agent models all right? Whereas there's just one agent who represents the whole generation or the whole country. The representative agent models are indifferent to distribution within the category represented. So the distribution within a generation is just not, it just disappears in the Stern models. So as I say, within a generation, you're ignoring differences between the rich and the poor regions in that generation, those which are more affected by sea level rise, drought, etc. So choosing to ignore distribution is value laden. I mean, we might return to the issue later on, but I mean, this model is going to conceal problems of distribution. Fourth, choice of weights. So you've got this maximize expected utilities framework, you're going to maximize this expression, you've got these weights in it for each generation. How do you assign weights to the generation? Well, that turned out to be a very heated issue in the Stern review. Stern thought each generation weighed equally. Stern and the rest of the committee there. But how do you assign it? I mean, you can pretend it's not there, and that's just weighting everything equally. Maybe if you put a 1 in, right, the W disappears, but that's a choice. Do you use equality of generations? If there's inequality, why? Okay. So again, any choice is value laden. Okay. So that's really, I wanted to provide an example about how value laden most modeling activity is in the social sciences at least, but I also think this is not peculiar to the social sciences. It's going to be value laden when your models are going to be used to intersect the world. Okay. So if you build a laser, you're going to have some of the same problems, but there'll be much more, a laser model, they might be more buried. Now, second is finding objectivity. So I want to explain about objectivity to be found. When models affect the world, I just want to claim and hope that you are on board with this. There's a duty of care to be objective in your modeling. A model is not objective in the sense that I want to draw our attention to unless it gets it right. Now, getting it right means that the model does what it's supposed to. So let me go back a minute, because I've realized on reflection, looking back at the slides, that this gets it right is shorthand, and the shorthand, since you're seeing it written, might stick in your mind rather than what I'm about to explain about it. There's a very peculiar, odd, redundant English expression. We want here the objective facts. Well, as if there were possible to have unobjective facts. So we want here the objective facts. It's objective in the sense intended there that I want us to focus on. And what it means there, we want the objective facts, is we don't want just any old fact claims you happen to be willing to offer us. We want fact claims that are backed in the right way, that makes it likely that the fact claim is reliable. Okay. Now, the point about reliability is it immediately invites the question, reliable for what? So as soon as we start thinking about wanting objectivity in the sense that we want our models to be backed in the right way to make it likely they're reliable, we have to ask about reliable for what. So now we have this asking, so getting it right in this sense is going to mean that the model, you're aiming to get it to do what it's supposed to. And that introduces a wrinkle, and a really serious one. So if the world model is going to be, if it's going to be world affecting, in which case, if it's going to be world affecting, I think we do have a duty of care, then it becomes a very complex matter about what the model is supposed to do. And it's not obvious. That's what I want to discuss now. So what the model is supposed to do involves the right purposes, those that the model should serve. So getting it right intertwines, again, the epistemic and the moral. And this is a lesson that many philosophers and scientists have been urging anyway, but in particular, the two people that have been influential in this objectivity literature are the philosophers of social science Sharon Krasnow and Eleonora Montusky. Okay, so I want to consider now thinking about duty of care and objectivity as a duty of care. It's related to Spanish concepts that I'm not going to try and pronounce, which is one that apparently is translated due diligence and diligence of care. The demand is what the law or good sense dictates. That's what a duty of care is, both as I understand it in British Anglophone law and in Spanish. And what good sense dictates may not be, in fact, generally isn't and often should not be explicitly stated. Should not be explicitly stated because the notorious thing we know that you can write you can write everything and somebody can always find a way to do the letter of the law but not obey the spirit of the law. So it's not explicitly stated. And individuals or corporations are potentially liable to be negligent, be accused of negligence when they fail to exercise good care to fulfill this duty. Okay. And as I said, lists can give examples, but they can seldom be exhaustive. So you're given a duty of care as a bank clerk. There may be some examples of what you should do, but a new customer comes in and really you should have realized that was not the way to treat them. Okay. So now let's think about a duty of care. In general, what's required for duty of care? In English tort law, I'm now going to read to you, there must be and is some general conception of relations giving rise to a duty of care, of which the particular cases found in the books are but instances. So when they give you examples, those are but instances. The reasonable person is sometimes described as the man in the street or the man in the Clapham omnibus. Such a man, taking a ticket to see a cricket match at Lord's, would know quite well that he was not going to be encased in a steel frame to protect him from the 1 in a million chance of a cricket ball dropping on his head. So that's a bit what. So the point is that nobody tells you what's required. You have to find it yourself, which is how we come to the idea of objectivity to be found. And this idea originates with Eleanor Montusky, and she and I and a few others have co-authored the book that Carl said is forthcoming, and we discuss objectivity to be found in the book. But the idea originates with Eleonora, who also is responsible for the Vaillant Dam example. Okay, so objectivity in modeling is a demanding duty when it's a duty of care. Okay, it's always demanding to be objective in your modeling or in your scientific practice. But what we wanted to argue was that it's especially difficult when it's a duty of care. It's your responsibility to find the models that serve the purposes, to use the right methods, right? But you have to find the right methods. But you also have to find the right purposes. So you want the models to be reliable for the purposes, but you have to also see to it that they serve the right purposes. Okay. And so let's just spend a few minutes looking at the Vaillant Dam disaster as an example. The disaster on the 9th of October 1963, 260 cubic meters landslide fell from Mount Tauk behind into the reservoir. The dam withstood a force 8 times what it was designed for, which was an engineering triumph. Virtually, though, the entire reservoir blew over the dam, destroying Langroni and severely damaging other villages. As I said, it killed over 2,000 people. Was Vaillant modeling objective given the duty of care? Well, it wasn't criminal, and that's been reviewed. Okay. The problem is it wasn't unusual. I'm going to return to this, but the failures that happened in Vaillant Dam modeling were probably failures that if you'd substituted some of the engineers for other engineers, some of the planners for other ones, might well have made exactly the same failures. We have here what we think of as a failure of objectivity. the wrong models were developed and relied on because the wrong purposes had center stage. So that's the story that Leonora has, and we're telling about this. Now I'm going to tell you about the Vaillant Dam. I'm going to give a narrative. It's the conventional narrative. Every example is a hostage to fortune because there are probably other narratives, but just go with me. This is the standard narrative, and if it's the case, then it illustrates the points we want to make. Intertwining the moral and the epistemic, most effort focused on the formidable engineering challenge of building the dam. So that's what was center stage. A system of 146 equations was perfected and solved, and that was in order to build a dam that would stand and generate electricity. And that was, it did miraculously. Just 8 times the force it was built for it withstood. Safety purposes were not taken seriously enough in developing and assessing the models given the stakes. That's the bottom line here. So I wanted to tell you about sort of some of the things that happened. Probably go quickly because you get the idea fairly quickly. More than 3 years, there were land movements were monitored, and geologists did study the slopes. And some warned of a deep-seated landslide. Others said, well, there'll be a landslide, but not very bad. Small landslides, there was one early, 1960, those were expected. In 61, there was a small bypass tunnel constructed, just in case the reservoir was obstructed by a landslide to let the water out. Okay. In 61, calculations based on a small model of the entire reservoir suggested that a small landslide into the lake could generate a 30-meter high wave. Technicians suggested not exceeding the water level height that was actually surpassed in 1963. So even on the basis of this model, they filled it. So the first filling of the dam, it went up to 170 meters above river. At that, above the river, right, the water was filled up till that level. A 2-kilometer long crack appeared. There you see it, and that suggested a landslide had occurred. Okay. Then 1960, at 180 meters, 700,000 cubic meters of material slid into the lake in 10 minutes. The level was dropped then to was dropped from 180 meters to 135 meters. And that reduced the movement. So that sounded good, okay, at 135 meters, the land's not moving very much. The assumption here was that the movement of the large landslide mass could be managed by elevating the level in a careful manner. So we had it, if we went up too fast, if we just elevated it well enough. But they didn't really know how to model landslides. So there was a second filling and a second drawdown. The experiences gained from the second filling and drawdown confirmed the engineers that control of the landslide was possible by altering the level in the reservoir. There was a third filling and a third drawdown in September. The velocity with which the land was actually moving was 3.5 centimeters per day. In late September, then, there was a drawdown, and by 9th of October, it dropped 10 meters, and the velocities nevertheless slowly increased. And they actually were recorded up to 20 centimeters a day motion. Okay. Then October 1962, there we had the Vaillant Dam disaster. Now, what was missed out? Well, the major thing that was missed out was modeling landslides. The continuous rejection of the worst-case scenario was in part based on a lack of understanding of large mass movements at the time. They didn't know how to model them, but they went ahead anyway. Right? So modeling landslides. Prediction of multi-hazard slope stability events requires an informed and judicious choice of the possible scenarios. An incorrect definition of landslide conditions can lead to inaccurate predictions, wrong engineering and risk management decisions. Okay. So there were reduced scale experiments 2 years before the Vaillant disaster. They were carried out with a material not representative of the actual rockslide behavior, and they did not consider the simultaneous failure of the whole landslide body. Okay. So, based on these inappropriate assumptions, the physical models led to wrong estimates of the safety operational level for the dam. Okay. Now, I want to think about, just revert to the topic, which is objectivity and responsibility. What happened here was that we had an over-optimistic presumption that the modeling was good enough. We didn't know how to model landslides, but we fiddled and we did our best I can. But it should have been clear at the time that the modeling wasn't good enough. It was not what a reasonable man thinking seriously about the real dangers to people living down the valley would have done. They were relying on models of, first of all, let me tell you, the models that I mentioned at the beginning with the 146 equations, the models were actually used to build a dam that would stand. Right? Those models were really good and well backed up for the purposes the purpose of building a dam that would stand. It was that we then needed further models to figure out whether the safety of people down the valley was assured, and the modeling there was not appropriately backed up, given the huge human life that was at stake. So they were over-optimistic. They thought them acted as if the modeling was good enough. They relied on models of draw down and gradually refill, and that we think was not modeling objectively, not doing due diligence to get the right models for the right purposes. It was not modeling objectively given the huge moral costs. So again, here we see the intertwining of the moral and the epistemic. Okay, so now I want to leave you with some parting thoughts. I've urged that modeling objectively requires attention to what the models are supposed to be reliable for, and that goes beyond taking sort of what's immediately given and center stage and thinking about, I mean, no one would have denied that you should build a dam that was safe, but that kind of safety down the valley was not center stage. It was sort of happily assumed that if the dam stood, that people would be safe. Okay, so given those reflections, I do have some further parting thoughts. The Vaillant modeling, there was too much focus on a dam that stands, and too much optimism about models that predicted levels were safe given the stakes, and too much willingness to go with, we didn't know how to model landslides and went ahead anyway. Now, the question I want to leave you with was, who was at fault for the faulty modeling? Okay, I mean, who failed to be objective? Who failed to do due diligence in their duty to find the right models for the right purposes? Well, did the engineers lack appropriate intellectual humility in this case? I mean, were they just said, oh, well, we know what to do? Were they presuming without sufficient reflection that the models were good enough? I mean, is it the engineers at fault? I mean, they weren't good enough, sufficient given the costs of mistaken modeling. But the problem is that's more than one might expect from somebody who's hired as an engineer to build a dam, or a team of people. Most engineers, the reflections afterward have suggested, most engineers would have done the same. So objectivity then as a duty of care is a really heavy burden, right? Because you're told to be as objective as, if it's a duty of care, you're to be as objective as the reasonable person. You must take responsible care to avoid acts or omissions which you can reasonably foresee. So some individuals will be very bad at this. I mean, it's just, don't hire me as a bank clerk, and I don't have that sensitivity to it. And it's probably very difficult to find engineers who have, you can't be sensitive to everything. And some individuals will be very bad at it in general, and some will be very bad at it for finding, for certain purposes. Now, what I want to leave you with is this idea is, I've focused on modeling, and I've focused on, among other things, modeling the Vaillant Dam and modeling the Stern Review, but other models look different and they face different concrete problems, but I think the lesson's the same, that it's too easy for modeling to be biased, prejudiced, presumptive, right? And it's too easy for that to happen without notice or intention. Because modeling objectively is demanding, and it's more demanding than we usually represent it as. And I think that it is too demanding to put onto individual modelers. That which leaves me with the Vaillant Dam as a lesson in the need for institutional development, which is what I'm now trying to go around urging. It doesn't seem to me that, I've been at a lot of places where people say, let's get scientists to be more responsible and get them to think more about how their work is going to be used and things. I think that the responsibility of individuals is important, but it's not the core solution. Objective modeling is an institutional problem. And in conclusion, I really want to leave us with this question that I hope maybe the academia will help address, is what can we do to develop institutions that support modeling objectively? So, thank you.
Thank you very much, Professor Cartwright, for this illuminating lecture. It is a true honor for us here in Barcelona to have you as recipient of the Hipàtia Science Prize. We are now getting...
I said the honor is mine, thank you.
We are now getting to the end of the ceremony, and the City Councillor Jordi Martí will address the audience with closing remarks.
Okay. Thank you very much for your conference, and only a few words to say thank you. Thank you very much. I want to give my special thanks to Mrs. Cartwright for her presence today in Barcelona, and many congratulations for your award. It's a great honor to have you with us today. And also to say thanks to the 5 members of jury, Mr. Bjorn Wittrock, Genoveva Martí, Mrs. Genoveva Martí, Mr. Alexander Fidora, Mrs. Maria Dolors García Ramón, and Mr. and friend Ricard Guerrero. And I want to thanks to the people who speak today, this afternoon in the City Council, Ricard and Mrs. Marja Makarov, and Mr. Karl Heffer, and I want to thank Mr. Andreu Mascolell for his support and to improve the relationship between science and the city. For this city, for Barcelona, science is very important. It's very important for cultural development, for social and economical development, but I think it's important also for the science, the collaboration of the City Council and of the city in general, the city. And I think this moment, this special moment, this symbolical moment especially shows the relationships between science and our city. And I think it's very important for us, it's very important to be here with all of you, and thank you very much, our special invited tonight. Thank you very much.
So thank you, Mr. Martí, for these encouraging closing remarks. I would also like to thank the audience for having joined us in this event and the people who have intervened in it. And we have now reached the end of the academic ceremony, but it's not closing time yet, because for those of you who want to join us, there is a cocktail prepared here outside, just outside this hall in the Gothic Gallery, and you are all invited to join us. Thank you very much.